Hi, hello, very good evening, dear students. My name is Venkatesh. I am going to teach now effective atomic number. So, what is effective atomic number? So, how can you identify the effective atomic number? We will discuss in this topic, right? So, now, what is the meaning of effective atomic number? In order to explain the stability of the complex, Sedgwick proposed effective atomic number method. So, coordination complexes, stability. How can you expect or how can you identify the stability of the coordination compound? To identify the stability of the coordination compound, Sedgwick scientists proposed one method that is only we call as the effective atomic number method. So now it is defined as the number of electrons with the metal atom or ion. Number of electrons with the metal atom or ion after gaining the electron from the donor atoms of ligand. So generally in the coordination complex the central metal atom is accepting the electron from the ligand. Okay, or central metal ion is accepting the electron from the ligand. After accepting the electrons from the ligand, how many number of electrons are present with the central atom? Based on that, we can decide the stability of the complex. Right. So now, according to Sedgwick, after gaining the electrons from the ligand, after gaining the central metal atom or central metal ion, gaining the electron from the central, after the gaining the electrons from the ligand, number of electron decide the stability of the complex. Right. Generally, the effective atomic number coincide with the atomic numbers of the next inert gas in some cases. So generally what happens here, when the central metal atom is accepting the electron from the ligands, the number of electron with the central metal atom sometimes is equal to inert gases atomic number. So which central atom number of electrons, if it is equal to inert gas atomic number, generally that complex we are considering as a stability, or the complex we are considering as a stable according to effective atomic number. So which molecule in which coordination complex the central atom number of electron, if it is does not equal with the inert gas atomic number, generally we are considering the complex is not stable or the complex is not following the effective atomic number method. So once again I am saying that generally in the coordination complex, central atom and ligands is present in the coordination sphere. The central atom or central ion, central metal atom or central metal ion is accepting the electron from the central atom. When the central metal atom or ion is accepting the electron from the central, accept the electrons from the ligand, the total number of electrons with the ligand is equal to, if it is inert gas atomic number, any one of the inert gas atomic number, generally the complex we are considering as a stable. If the number of electron with the central metal atom is not equal to atomic number of the inert gas, generally we are considering the complex is unstable or the complex is does not following the effective atomic number method. So we will discuss some examples, based on that we can understand it clearly. So now here generally we are discussing the one example, K4FeCN6. K4FeCN6 hexacyanate potassium hexacyanate ferrate ion, generally K4FeCN6. So I'm writing the here what K4FeCN6. Before that writing the formula, before that writing the complex formula, I am writing the formula to identify the effective atomic number. So effective atomic number is equal to atomic number of the central metal atom. Atomic number of the central metal atom. Atomic number of the central metal atom. Atomic number of the central metal atom minus, okay, because the number of the atom central metal atom may be sometimes available as a atomic form, sometimes available as a ionic form, that is depend on the ligand. So if it is available in the ionic form, always it is available in the cationic form, that means it is loses some fixed number of electron. So now atomic number of the central metal atom minus number of electron lost by the central metal atom. Number of electrons lost by the central metal atom, CMA, plus number of electron gaining by the ligand, or number of electron gaining from the ligand. Number of electron gaining from the ligand. So number of electron gaining from the ligand. Number of electron gaining from the ligand. So this formula, if you remember, you can identify easily the central metal atom in the coordination complex, it will be it will be follows the effective atomic number or not, or we can understand easily the complex is stable or not by this formula. So what is the formula? Effective atomic number equal to atomic number of the central metal atom. Every central metal atom or every metallic atom generally having the atomic number. In the coordination complex, you have to write the central metal atom number. After that, the central metallic atom, how many electrons is losing? To get that many electrons. So atomic number of the central metal atom minus number of electrons lost by the central metal atom plus number of electron gaining from the ligand. How many electron gaining from the ligand? You have to write that. So if it is equal to inert gas atomic number, the complex is stable, the complex is follows the effective atomic number method. If the number is not equal to inert gas atomic number, it does not follow the effective atomic number, and we can say that is not a stable, right? So we'll see the example by this formula. The example is K4FeCN6. K4FeCN6. So the formula is K4FeCN6. Right? So the formula is K4FeCN6. Here potassium is a cation and iron is the central metal atom and cyanide is the ligand. So cyanide is a monodentate ligand. Cyanide is a what? Monodentate ligand. That means the cyanide can donate one electron pair to the central metal atom. One cyanide donate the one electron pair to the central metal atom. So that means how many ligands is present here? 6 ligands is present. 6 ligands donating the 6 pair of electron to the central metal atom. So now, what is the central metal atom oxidation number here? So iron oxidation number I want to find. So I am taking the iron is a X. Now potassium charge is what? Plus 1. So how many potassiums are there? 4. So that means plus 4. And cyanide is monodentate ligand. That means it is having the charge is negative, minus 1. So how many cyanides is present here? 6 cyanides is present. So that means minus 6 is equal to 0. So my 4 minus 6 is what? Minus 2. Then x minus 2 is equal to 0. That means x equal to 2. That means iron charge is plus 2. That means iron oxidation state is plus 2. That means iron is losing how many electrons here? 2 electrons is losing. So number of electrons losing by the central metal atom is 2. Number of electrons losing by the central metal atom is what? 2. And the iron atomic number is 26. Iron atomic number is what? 26. So the atomic number of the effective atomic number formula is what? Effective atomic number is equal to atomic number of the central metal atom. Atomic number of the central metal atom is 26. Minus number of electrons losing by the central metal atom. How many electrons losing? 2 electrons losing. Plus number of electrons gaining from the ligand. How many ligands is present here? 6 ligand is present. So each ligand donating 1 electron pair. 1 electron pair nothing but 2 electrons. So totally how many ligands is present? 6 ligands is present. 6 ligands donating 6 electron pair. 6 electron pair nothing but how many electrons? 12 electrons. Right? So now 26 minus 2, 24. 24 plus 12 how much here? 36. So effective atomic number of this complex is what here? 36. So effective number 36 nothing but 36 atomic number is which gas? Krypton. So that means it is having the what? Effective atomic number is equal to inert gas atomic number. So that means we can say this complex is stable. What you can say? We can say this complex is stable, right? And it is following the effective atomic number method. So this is the one of the example, and the second example is, second example is FeCO5. FeCO5. So this is the what complex is FeCO5. Right here. CO is what? Neutral atom. This is carbon monoxide. CO is the carbon monoxide. Iron is the central metal atom. CO is the ligand. Iron is the central metal atom. CO is the ligand. So CO is what? Neutral ligand. CO is a neutral ligand. CO is a neutral ligand. So neutral ligand nothing but does not have any charge. So that means we can say the charge is 0. If the carbonyl charge is 0, automatically iron charge also 0. That means iron oxidation state is 0. Iron oxidation state is what? 0. Iron oxidation state 0 nothing but iron does not lose any electron. So that means iron atomic number is what? 26. So effective atomic number, central metal atom atomic number is what? 26. Minus any electron is losing? No electron is losing. Then plus how many electrons is accepting? Carbon monoxide, it is a monodentate ligand. That means it is donating the 1 electron pair to the central metal atom. So totally how many carbon monoxides are there? 5 carbon monoxides are there. So each carbon monoxide donating 1 electron pair, then 5 carbon monoxide donating the 5 electron pair. 5 electron pair nothing but how many electron? 10 electrons. So that means 26 plus number of electron gaining from the ligand is 10. Then 26 plus 10 equal to what? 36. Again it is showing the atomic number of krypton. That means effective atomic number of this complex is equal to which atomic number of the inert gas? Krypton atomic number of the inert gas. So we can say this complex is stable. We can say that is what? This complex is stable and this complex is following the effective atomic number method, right? So one more example we will discuss. So one more example, that is a copper. So copper is a central metal atom and the ligand is, copper is the central metal atom. Copper is a central metal atom and the ligand is ammonia, right? So how many ligands is present here? 4 ligands is present. And one counter ion is present, that is SO4. One counter ion is present, that we are saying as SO4. Okay, whatever the species is present within the square bracket, that we call as a coordination sphere or coordination complex. After the square bracket, what is present, we can say there is the counter ions, right? So now here, this is the complex. Now we want to find that copper oxidation state here. So ammonia is what? Ammonia is a neutral molecule. Ammonia is a neutral, that means zero charge. So SO4 is what? SO4 coming from the H2SO4. Okay, so now H2SO4, from the H2SO4, SO4 is coming. That means it is sulfate. Sulfate charge is what? -2. Sulfate charge is what? -2. I want to find the copper oxidation state. So copper oxidation I don't know. I have to find. So now it is the X. X place here what? Neutral. That means 0. Okay, so it is a 0. So next of all what? SO4 is -2. That means X -2. X minus 2 is equal to 0, then X equal to what? 2. That means copper oxidation state is a +2. Copper oxidation state how much here? +2. That means copper losing, how many electrons losing? 2 electrons are losing by the copper. So then copper atomic number how much? 29. 29 is the copper atomic number. So now effective atomic number is equal to atomic number of the central metal atom 29 minus number of electrons losing by the copper. How many electrons losing? 2 electrons is losing. So -2. Next one place, number of electrons is accepting from the ligand. So what is the ligand here? Ammonia is the ligand. How many ligands is there? 4 ligands is there. So ammonia is the monodentate ligand. That means it can donate 1 electron pair to the central metal atom. So monodentate ligands, how many is there? 4 is there. So each ligand donating 1 electron pair. Totally 4 ligands is present. So 4 ligands donating the 4 electron pair. 4 electron pair nothing but how many electron? 8 electrons. So that means what? 29 minus 2 and plus 8. So 29 minus 2, 27. 27 plus 8 how much? 35. So effective atomic number of this complex is 35. So 35 nothing but, is it any inert gas? No, it is not an inert gas number. So that means we can say, according to Sidgwick, this complex is not stable, or we can say that the complex is not following the EAN method. So finally what you can say, in the complex, the central atom EAN value, if it is equal to inert gas atomic number, we can say that the complex is stable and the complex is following the effective atomic number method. The central metal atom effective atomic number is not equal to inert gas atomic number. We can say that the complex is not stable, otherwise the complex is not following the EAN method. So this is the simple way to identifying the effective atomic number of the central metal atom in the coordination complex. So this is the topic, and thank you. The topic is completed, and we will send the